Hello, I'm Allison Patton, a senior scientist at HEI, and I'd like to welcome you to our virtual workshop on health applications for satellite-derived air quality. This is session 4, a roundtable discussion on the future of satellite remote sensing of air quality and health applications. Before we begin, I'd like to remind you that all attendees are muted in view-only mode for the duration of the webinar. Please submit your questions via the Q&A function at any time. And if you experience any logistical difficulties, please contact us using the chat box. We'd like to hear from you about your work on satellites, air quality, and health via the survey shown on the slide and in the chat. There's also an opportunity there to sign up for future communications from HEI on this topic. The webinar slides and video from today will be posted on the HEI website. For those of you who haven't joined any of the previous webinars and who are new to HEI, I'd like to briefly introduce the organization. We're an independent nonprofit corporation chartered to provide policy-relevant, high-quality, and impartial science. We're funded jointly by government and industry and fund research that is selected, conducted, overseen, and reviewed independently of our sponsors. We do not take policy positions. We have a series of research reports, some of which that might interest this audience are shown on the screen. This workshop falls under the purview of the HEI Research Committee. The Research Committee works with HEI on strategic planning, defining research needs and requests for applications, and selecting and overseeing funded studies. The workshop is being conducted to inform the Research Committee's next steps in this area of satellites, remote sensing, and air quality and health. The two chairs for this workshop are Dr. Jeff Brook and Dr. Heather Holmes, and they're both here representing the Research Committee as well. This is the final webinar of a 4-part series. The slides and recordings from earlier sessions are available via the workshop webpage or on the Health Effects Institute YouTube channel. I'll take a few minutes now to remind us all of what was discussed in the previous session. We started with a set of guiding questions. What opportunities do satellite-based products bring for advancing knowledge on air quality and health, and what are the challenges? What's coming in the future from satellite observations? And can those new technologies address some of the existing challenges? How well do we appreciate the limitations of satellite products, and how does that fit into our interpretation in the context of health impacts and burden estimates? Finally, how far can we take satellite products to inform studies of health effects of air pollution? Session 1 set the stage for the conversation. Presenters introduced satellite remote sensing, gave a detailed description of how satellite data have been used for exposure assessment in a recent epidemiological study, and described how capacity is being built for application of satellite data across many fields. The speakers explained how the diverse needs of the audience inform how satellite data should be combined with other data sets and what spatial and temporal resolution are needed. Hot pot and baking metaphors were used to highlight the level of thoughtful consideration of inputs from many disciplines that is needed to prepare a recipe that is appropriate for a specific application. And satellite-derived air quality and health is a growing field where the right toolbox and audience will be needed to move the field forward, both with the Maya mission, which is the first satellite mission designed with health applications in mind, and in other ongoing and future missions. Session 2 explored ways in which the potential of satellite-derived remote sensing of air quality is beginning to be achieved around the world. We started with an overview of how satellite, ground, and model-based data are combined to enhance the value of air quality information on industry sectors, pollutant sources, and particle composition. Then we explored exposure assessment and health burden assessment with a specific example of wildfire smoke. Next, we had examples of how satellite-derived air quality products are being used in 3 countries. In India, satellite PM2.5 products are being used for air quality management and health impact studies. In Colombia, biomass burning contributes substantially to ambient particulate matter, but mainly in locations far from monitoring stations. So satellite-derived air quality data are being used to explore the health burden from PM2.5. In South Africa, data on emissions and on pollutants other than PM2.5 are scarce, and satellite data help to constrain emissions and measure trace gases. Presenters discussed the value of open, available, and consistent data in citing ground-based monitors, tracking air quality trends, and contributing to better exposure models. They noted that the best information available should be used to inform good policy, that some of their analyses were only possible with satellite data. Centering local priorities, building local technical capacity, and working with scientists in different regions were highlighted as important aspects of using satellite remote sensing data in studies of global health and air quality. Session 3 delved into pushing the methodological limits on satellite use in health applications. The session started by noting that air pollution observed from space reflects real-time changes in emissions and has high correlations with ground monitors. It was noted that satellites, models, high-quality sensors, and low-cost sensors provide complementary information, and none of these sources of data replace any other source. Then we saw some initial data from GEMS, the first geostationary satellite in a constellation that will cover the Northern Hemisphere. The constellation will eventually be completed with the launches of Sentinel-4 over Europe and Tempo over North America. After having focused mostly on large-scale applications, we ended with a look at the ability to apply satellite-derived air quality data to questions related to exposure and health inequities within a city, and to inform decision-making related to air pollution health disparities. So in the first 3 webinars, we have explored some of the current and future capabilities of satellite remote sensing for air quality and health applications. That brings us to today's roundtable discussion to summarize and synthesize the main research needs to make the best possible use of opportunities to apply air quality data from satellites in trusted, high-quality health research. Dr. Heather Holmes will now open the panel discussion.
Thank you, Dr. Patton. I want to welcome all of you that are attending virtually today to our roundtable discussion. I also really want to thank the speakers in the first 3 sessions of this workshop series because they nicely set the stage for the discussion we are about to have. The first satellite that provided information to improve numerical weather prediction was launched in 1960. Fast forward 60 years later, and there are numerous types of satellite retrieved products used in weather forecasting today. Some related to the atmospheric state, like temperature and cloud information, and others related to the land use characteristics like surface albedo and vegetation. It's very natural that the air quality community followed down this path of remote sensing from spaceborne satellite observations. For the last 2 decades, satellite missions focusing on the gas and particle composition of the atmosphere have provided many useful data products for different pollutant species. And perhaps more importantly, this drastically improved the spatial availability of air quality information. This is critical in locations around the world that do not have air quality monitors, but yet have high levels of ambient air pollution that adversely impacts the health of people living in those areas. As we've moved forward with these satellite products as a community, there have been many strategies to maximize their usefulness. Often this means that the satellite products are combined with other types of information like air quality models or ground-based monitors. Really, combining these different types of data is done to maximize the usefulness of all of these types of data. A unique aspect of the satellite products is that they are available globally and provide a spatial snapshot of the distribution of ambient air pollution that we cannot get from ground monitors alone. Because of this uniqueness and the utility that this information provides, it makes sense that, like the weather forecasting community, the air quality community will continue to make advancements in this area. From new remote sensing platforms that are already planned and being developed, to algorithm improvements that are constantly ongoing, and then on to the end user community that finds new ways to incorporate these products into different research areas. Today, I'm looking forward to the open discussion with input from researchers across so many different disciplines that we will have related to the use and limitations of satellite products in health application research. Right now, I would like to invite all of our panelists to turn on their cameras. And to begin, we will introduce each panelist and have them give a short prepared statement related to their background and experience using satellite-derived air quality products. After these short statements, we will open the discussion. We will start with Dr. Eloise Murray from the University College London.
Thanks, Heather. So I'm an atmospheric chemistry transport modeler, and I develop, test, and also evaluate satellite data products and apply these with models as well as ground-based observations to estimate emissions of air pollutant precursors and also determine long-term changes in air quality over cities. So I've done things like estimate ammonia emissions from agricultural activity in the UK to determining that air quality is degrading rapidly in cities across the tropics. And the main strengths of satellite observations that make them appealing to the research that I do is that they're long-term and consistent. Many of these instruments have been in space for more than a decade. And they can provide us with information about air quality where there are no surface observations or where access to the data is limited or where there's concerns over the quality of the data. And the other advantage is that they provide measurements of the whole atmospheric column covering greater geographic extent than the surface observations. So we can more closely relate these to precursor emissions than we could with the surface measurement networks. But one of the main challenges, and of course, associated with satellite observations is that there are limited appropriate observations to evaluate them, as well as the models that are being used to retrieve the data products that we end up using. And just to highlight that the most successful and impactful research that I've done that's used satellite data products has resulted from collaborating directly with the data providers from the start of the project, as this aids in understanding the detailed steps that are involved in deriving the satellite data products, the inherent uncertainties in the retrieval steps, as well as the user-specific data quality checks that need to be conducted when using the satellite data products.
Thank you very much, Eloise. For those who have questions or comments, please enter them in the Q&A. Our next panelist is Colette Heald, who's a professor with expertise in atmospheric chemistry from MIT.
Thanks, Jeff, and thanks for the invitation to be here. I'm looking forward to this discussion. So we were asked to address a few questions. As Jeff said, I'm an atmospheric chemist, and I work, like Eloise, primarily with 3D models. We use a lot of observations in my group, and that includes satellite data to test and improve model descriptions of aerosol life cycle, among other things. I'm going to focus maybe my comments today on aerosols. We occasionally estimate premature mortality of PM2.5 as a metric to characterize the impacts of trends or sources that we're exploring. So in terms of the strengths of satellite-derived air quality, as Eloise already said, I mean, the ability to observe the temporal consistency, of satellite monitoring that provides trends, I think is hugely important. And the ability to observe globally, particularly in regions with little to no surface monitoring, obviously is a huge value. And on the horizon, I see opportunities with geo observations to also tell us more about chemical regimes that could provide insight into secondary pollutants. So that's pretty exciting. But of course, it's really important to note that with the geostationary measurements, those are not going to be global. So that only gives us a snapshot on certain regions of the world. With regards to the challenges or pitfalls, particularly in the case of PM2.5, I think there's a threefold challenge. The first is the conversion from what satellites observe, which is AOD, to what is being used in the health studies, which is surface PM2.5. And that itself relies on some sort of model. So that can be a 3D model, a land use model, a machine learning model, all of these together. And there are a lot of uncertainties in the aerosol life cycle, particularly for secondary aerosol, that are not really just well described in all of these models. There are challenges in understanding these processes mechanistically. It's hard to come up with land use parameters that would be good proxies for secondary aerosol. So I think that's a challenge. Another challenge is that I don't think we have a good strategy for evaluating the quality of high resolution derived products. So low-cost sensors offer some hope here, but they're not without their own challenges. And particularly, I think there's some desire to use these kinds of data products for environmental justice studies. As Sally Posetti showed us some great examples for NO2, it's not clear that the relative distributions of derived PM2.5 are accurate. And it would be great to think about a strategy for looking at that. And then, of course, the third challenge is communicating these uncertainties between communities. And I think, as Eloise articulated, this is always going to work best when you have a strong collaboration between, the users of the product and the developers of the product. One other final point I wanted to make is that, satellite drive PM2.5 has been used extensively over the last decade or so, but I think we're also at the point where we should be asking how far we can take PM2.5. And differential toxicity suggests that what we really need is speciated PM2.5 observations, and satellite can't give us really sources or composition of PM. And so to start asking the questions about what is the path forward and what opportunities there might be to use satellites in thinking about that. I look forward to the discussion. Thanks.
Thank you, Colette. And now I would like to introduce Dr. Tracy Halloway from the University of Wisconsin-Madison.
Well, thank you so much. And it's really a pleasure to be here. I'm really speaking from the perspective of my role leading the NASA Health and Air Quality Applied Sciences team. And for about the past 10 years, the NASA Applied Sciences program has been investing in a team-based initiative to really be a bridge between satellite data products and analysts and user communities in air quality, health, land use, energy, anybody who could benefit from satellite data applications. And my own background is pretty similar to Colette and Eloise. I was trained as a 3D atmospheric chemistry modeler, but I did my postdoc in the School of Public Health at Columbia University. And for a long time, I've been trying to think about how do we use these advanced data and tools for new applications. And there's really no better example of that challenge than when we're thinking about how to use satellite data way up in space that sees the whole atmosphere for nose level concentrations of what people are breathing and exposed to on the ground. And like Colette, I really sort of approached this from the perspective of three different issues that I think all are barriers, but all also offer opportunities for advancement. And these are the technical issues, the conceptual issues, and the communication issues. And I think a lot of attention, very reasonably, is focused on the technical issues. How precise are the satellites? What is their resolution? How well do they compare to ground-based measurements? And what are NASA and other space agencies doing to advance the science and technology to detect more species and better? And those are really important questions. But I would say that actually, I think that we've had a lot of the most traction and progress on those issues, and a lot of new initiatives and missions are already in the pipeline that will be moving that forward. So then when we're thinking about the conceptual issues is really how do we use the data that we have, and how do we best use next generation data to address health-based problems. And really whatever's coming from the satellites is not apples to apples with ground-based monitors. So it takes a new way of thinking about how to interpret, point-based versus spatial footprint. This issue came up with Jeff before this meeting, thinking about what questions are well suited for remote sensing and how to make the best use of data from models, satellites, and monitors. And finally, the communication issue, building awareness of the data products that are out there and recognizing that we want to have many users, like thousands times more users than we have developers. So how do we make those products user-friendly to plug in to analysis approaches that the health community already has? And this is a challenge because there's so much terminology and jargon on both sides of the health and air quality and remote sensing communities. but also barriers with data formats. So it's really exciting to be part of this HEI panel and to have participated in these sessions where the health community is really leading these discussions, and excited to see where this conversation goes.
Fantastic, Tracy. Thanks very much for your insights. I will now introduce our next panelist, and that is Laura Judd, who's from the NASA Earth Sciences Division. Please go ahead, Laura.
All right, thanks, Jeff. Good to be here, everyone. I wear two hats at NASA, which both connect to satellite remote sensing and air quality expertise more so than health. But the one hat that I wear is I'm an associate program manager for NASA's Health and Air Quality Applied Sciences program. This program aims to lower the barriers in the use of NASA data, particularly satellite data, in public health and air quality management sectors. But I also work at NASA Langley Research Center as a research scientist, and I spend a lot of time thinking about the interpretation between satellite data, ground data, and aircraft-based data, particularly during field studies in regions that have high ozone. And so a lot of my perspectives come from thinking about ozone and ozone precursors like nitrogen dioxide and formaldehyde. So in reflecting in the strengths of satellite data, I echo a lot of what our panelists have already said today. Satellite data provides an unseen perspective outside of where other observations are. And what's exciting is that data is becoming increasing in granularity in space and time through new missions like TROPOMI, which is already up, as well as GEMS, which is already up, and NASA Tempo, which will launch next year. These observations are also testing the bounds of our knowledge of air quality at new scales, new spatial scales, new time scales, and I'm excited to see what we can learn going forward. And so, as everyone's already alluded to, satellite data doesn't come without barriers. I kept it to 3 points here, but can talk about more in the discussion. But as is said by everyone so far, I think, and every day during the webinar series, is really the idea that satellite observations are an integrated value through the atmosphere rather than at the ground level. Though that integrated value can be helpful, often what we want to have is what is the air that we're breathing, and accounting for that is a challenge, but not insurmountable, as we've seen. Satellite observations are also limited by the species of pollutants that they can measure. For example, under the regulated pollutants by the EPA, of course, ozone, surface ozone is a popular one. Satellites really cannot resolve near surface ozone. And so that can be a challenge. And probably the biggest barrier for new users is really data formats and volume. But the Applied Sciences program at NASA tries to help with these, like through teams like HeyCast, like Tracy is leading and can speak to. Programs like RSET, which was talked about by Ana Prados, I think on day one of these webinars, and early adopters programs through these new missions. So some of these missions haven't been around for decades, such as Tempo and Maya in the future, but there are programs that are trying to train users before launch. So hopefully you all learned about some resources through this webinar and through today. But I think the best thing that we can do to excel at using satellite data and health applications is to recognize the need for multidisciplinary teams and multi-perspective data sets together. And I'll end by just saying thanks for having me here, and I look forward to the rest of this discussion.
Thank you, Laura. And now I'd like to introduce our last panelist, Dr. Yang Liu from Emory University.
Thanks, Heather, and thanks for the HEI to invite me to join this panel discussion. I came in contact with satellite data in the year 2000, right after the launch of the Terra satellite. So it has been over 20 years. I'm an environmental engineer by trade, so I first view satellite data as a tool. It took me several years to learn to use it in particulate matter exposure assessment. Then I started applying this to the study air pollution health effects in collaboration with many epidemiologists. And in this process, I realized the limitations of existing satellites and their products. So I started working upstream to modify existing products. For example, I was the alpha user of the Modi's Mayak aerosol product before it became public. And I'm also working on creating the level 2 and level 4 PM products for the upcoming Maya mission. Now, we have seen many strengths of the satellite data during the first 3 sessions of this workshop. A particular strength in the context of air pollution epidemiology is that satellite-based exposure data can be matched to historical human health data collected for other purposes. So I want to talk a bit about the pitfalls in health applications. My experience is that most epidemiologists and health scientists don't know the technical details of how satellite data is translated into air pollution estimates. This is simply not part of their training or their job. Satellite-derived air pollution data is tricky for at least 3 reasons when you try to apply it in the epidemiological settings. First, satellite remote sensing itself is half measurement, half model. So as Colette alluded to, that it has many sources of uncertainties that kind of trouble epidemiologists. Second, we have seen an explosive increase in air quality data generated by black box type machine learning algorithms. These models claim to have very high performance, but it's hard to interpret. Finally, there are no curated data archives with health applications in mind to serve as benchmarks. So people don't know what to expect when they encounter a new data product. And the point I want to make is none of these challenges are going to disappear overnight. So my suggestion is if you are interested in pairing a health data set with gridded air pollution exposure estimates coming out of a satellite, satellite remote sensing, make sure the methodology of the data production has been published in a reputable peer-reviewed journal, so you can at least partially trace back the technique involved in the data production. It will be also very helpful to ask a exposure modeler to assess whether satellite data is the right thing for you. This type of people used to be a rare breed. They're hard to find. But now NASA has supported the HACAS team for 3 cycles. And HACAS has many experts in its family and extended family to help answer your questions. And it's a free service for you to use. I'm part of HACAS. I'm part of the MISER and Maya science team. So I'm more than happy to talk to you. I'm sure the HACAS members are also happy to discuss with you sort of the utilities of the satellite data that you have in mind. And with that, I look forward to today's panel discussion. Thank you.
Okay, wonderful. Thanks very much, Yang. Great set of panelists we have here for discussion today. I do note that it's interesting how the fields you've all come from are much more, I think, from atmosphere and engineering, and we don't have those who are deeply involved in the health and the epidemiology, though they're in the audience, and I expect we'll ask questions. One of the questions I see there now that alludes, I think, a bit to a point that I think came up in Tracy's presentation was around the differential toxicity question and moving beyond PM2.5 mass. Now, PM2.5 is an indicator. It's always been in my mind an indicator of some aspect of air quality. But getting to the next level of differential toxicity, which is a major question in the health research area, is a challenge. Hybrids of CTMs and predictions, perhaps measurements and satellites are helping to fill those gaps, but they're kind of a combination of resources again. So the question is really about more creative ways to use satellite data to infer things about major PM2.5 species, since it's not something that's directly observed. I have a sense that perhaps one path forward might be to look at areas where you have sort of known sources and you can know something about the emissions of the sources, from which you can sort of use the satellite data to isolate regions of impact of different types of composition. Perhaps it's some sort of hybrid source apportionment efforts that might be useful. What do you see? Maybe start with Tracy in terms of ways you might go into inferring composition.
Well, I might pass it to Colette because I think she was the one who brought up the differential toxicities.
Colette, okay.
Thanks. Happy to take a stab. It's a hard question though. I think, right. So I think fundamentally from, a satellite perspective, especially in the examples that were brought up in the question, sulfate, nitrate, ammonium look pretty much identical to the satellite, right? There's, the things that the satellite can differentiate are not composition, but the satellite can get a hint of size and sometimes when things are more absorbing or less absorbing as aerosols. So, but sulfate, nitrate, and ammonium really are scattering aerosols of a similar size. And so there is really no information from the satellite, I think, from AOD or sort of its derived components that can be used to differentiate those. So I think it's in a tough spot to sort of think about how can the satellite inform that. One strategy, I think, and I think it's just a sort of a question of as we move the data products forward and the quality of data, is the synergy with the gas phase measurements. And so, for example, NO2 combined with AOD might help you pin down nitrate. If we got SO2 retrievals, to beat down the noise, where we could use SO2 also, then we might be able to sort of differentiate sulfate. But I think that's a challenging and careful task that would need to be undertaken. And perhaps again, in the era of geo, when you can sort of also start looking at diurnal variability, there might be some promise in taking some sort of approach there. And I don't know if others like Yang might also have some thoughts on this.
Yeah, I think I'd see an interesting angle there from the combination of trace gases and aerosol that might infer composition. Has anyone been thinking about that on the panel or seen any work in that area?
I can comment a little bit on that. Well, I think it's an interesting idea. If you view the differential toxicity as some kind of a source apportionment, right? We're trying to introduce multiple pieces of information to learn, to kind of solve multiple unknowns. So I guess the combination of trace gas plus aerosols, not just PM 2.5, if you can decompose it further to say absorbing aerosols, not absorbing, spherical, not spherical, whatever. It's just kind of a different mapping of the same properties of the atmospheric mixture. A caveat there, though, for health applications is when you get into multi-pollutant models. For example, there is emerging evidence that NO2 itself has standalone adverse health impacts. Now, if we use NO2 to infer the composition of a PM somehow, or inform the composition of PM, and then later on bring in NO2 estimates as a covariate, then we're double counting the impact of NO2. Right? This is something to consider when we're dealing with air pollution mixtures. But I think what I like about epidemiologists is this group is very, very exploratory and they're super tenacious. I guarantee we'll find a way to figure this thing out.
Other panelists have any comments on that? Okay.
Can I just follow up actually on Yang's comment too? Because I think that reflecting on what I said, I think that is the important key point here, is that anything that you would do involving, merging different data products is going to lead to, a qualitative to some degree product, right? And actually explaining that to the user and how it can be used, I think is just a whole new level of challenge, right? So one might be able to use this to sort of provide indications of the composition of PM 2.5, but then I think one would want to be really cautious about how you would want to apply it then, right? And to make sure that you design the, that the epidemic, there isn't a mismatch in terms of the quality of what you've derived and how it's going to be used.
Yeah, and maybe just I'll dovetail off of that, because I think that, one Yang made this point that health users of satellite data, it's not their job to know all the ins and outs of where it came from. And I totally agree. But it is such a challenge, because when, a product is put out from NASA or from a space agency, that really has so many different pieces involved, than to say, well, this is satellite data and it's not a model data, when really it's a combination. And I think a good example is the planned data products from the Maya instrument are reported, there's going to be high resolution speciated PM coming out of Maya. But that's not just coming out of Maya. It's going to be a assimilated data product with a high resolution chemical transport model. And that's a very valuable data product, but it's not, some satellite observation akin to a ground-based instrument. It's a merged data product. And, I think this question about how in the weeds do health users want to get, and do they need to get to effectively use these new data sources.
Thanks, Tracy. I mean, I think I heard some really good words of caution there for how far to use these things, and it's very tempting to say, hey, I've now got all these species from Maya, and run off and use them. But it is a combination of a model where you input into the model the source receptor relationships, and then go back the other way and say that it's an observation based approach is not quite right. And of course the double counting and separating species as well. I think that really does speak clearly to the point that was raised by others, and Laura, I think, about working together in disciplines. Now, one of the things that didn't really come up, and we certainly know about the limitations and the levels of detail that people might want to know. But maybe panelists want to comment on something that we tend to forget, which is satellite data are largely all daytime. And we're missing the nighttime completely. Nighttime urban air quality is exceptionally complex to deal with in terms of the stratification of the lower atmosphere, differences in atmospheric chemistry. I've heard at one time, talk about, hey, we're going to start to use moonlight to look at AOD at night. What are your thoughts about, the nighttime limitations and what it might mean for health research?
Well, maybe I'll just get us started, because I think, to me, one of the most powerful ways to use satellite data is to help validate and evaluate chemical transport models, because we have models that provide spatially continuous data of all of the pollutants that we're talking about, and they provide it at the ground level where people are breathing. And so if we can use satellite data to build our confidence in the model results, to calibrate model results, to correct emissions, then I think that there's a way to be using these two different tools in a way that supports and advances health analysis. So, I think this idea that we don't have exactly what we need from satellites, we don't have ground level, 24-hour a day, every health relevant pollutant, but we have complementary data and tools. So I think even the idea of using satellite data with models, either to evaluate them or in an assimilated data product, I think that could really round the square, as they say, to get that 24-hour data that's needed by the health community.
Thanks. Laura, do you want to talk a bit about nighttime? Uh-oh. Did we lose Laura? Looks like she just dropped off. hopefully she'll come back in again.
I can add something, Jeff, while we're waiting for her.
Go ahead. Thanks. Colette.
Yeah, I'll pinch. Well, hopefully she'll be with us in a second. I was going to add to, I think nighttime is a great question, and I think it's a real challenge actually for thinking about air quality, because in general, we don't have like many observations at night, right? So if you think about field campaigns, those measurements are also rarely made at night. A lot of our ground measurements for some species are 24-hour averages and don't give us, or 3-day averages and don't give us, the diurnal profile. And these challenges that you mentioned about the diurnal, the profile, the boundary layer heights, how that's impacting surface air quality, those are very real and a problem I think that we don't adequately have we haven't addressed, because a lot of the observations don't provide us that information. So I think you're right to say that it's a sort of a thing, something that we're not addressing on the side. I suppose also a question I would have from an epidemiological perspective also though is, if people are inside mostly sleeping at night, then how do we think about sort of the outdoor air quality implications of sort of constraining that or not? So maybe that's a question that others have thought about. And now Laura's back, so maybe.
Yeah, great question. Laura, you dropped off, you must hit the wrong button, so.
No, I didn't. I actually lost connection, and I had something to say that was a follow-up to Tracy, so I'm not quite sure what was all said, but so apologies for my technical difficulties. Hopefully you can hear me now. But I think this is a really great question, and this what Tracy's response and what Colette, it sounded like you were alluding to when I joined. I only got the end of that, was satellite data isn't a one-stop shop at all. It's very limited in the species and the times of day that it can measure. And so we can't forget about the whole integrated observing system together, which does involve ground-based measurements for ground truthing, but also maybe more detailed measurements such as airborne measurements that are very detailed on the speciation. They can measure at nighttime, assuming it's not a remote sensing platform reliant on sunlight. And what those isolated detailed measurements can help us is learn what are the pitfalls in our chemical transport modeling as well. And so we can learn and be able to validate and evaluate those. But I would argue, I mean, it's for satellite data for a lot of, at least for trace gas air quality, it is limited to early in the afternoon. And a step forward before we think about night might just be, okay, we have all the rest of the daylight. We have these geostationary platforms going up. And so seeing how we can capture that transition from night into the day as we start getting those observations might be a next step before we think about the middle of the night. Or at least be able to, it's probably just not the realm of satellite data itself, but that's all I had to share on that.
Thanks, Laura. And important point was brought up there about where people spend their time, and maybe you're indoors at night and nighttime is not necessarily as important. That really brings clearly into the question of scale in all sorts of senses, whether it's spatial or time, and satellite's not going to help us crack into those things. There's no doubt about that. But it's always how you use it, not what can't you do, but what can you do. I heard a little mention about in terms of talking about speciation, about the current quality of sulfur dioxide from space, and we haven't talked a lot about SO2 in these sessions. We've seen examples of where you can see volcanic plumes very clearly, and I know that emissions work has been done around large power plants. What are any of your thoughts on where the status is for sulfur dioxide and its applicability for health related applications? Anyone spent some time looking at the?
Yeah, I mean, I think Colette said exactly the issue, right? We can't beat down the noise, so we're only seeing really, really large enhancements in SO2 coming from large power plants, coming from volcanoes. And this poses quite an issue when we want to look at parts of the world that have addressed their SO2 pollution, because we can't really trace it beyond really enhanced levels. And so we don't have very good constraints on the precursors of sulfate. But that's a problem with the surface observations as well. The sort of reference monitors, at least that are used in the UK, the majority are also experiencing this issue. SO2 concentrations are below detection, so we're even limited to using the surface observations, unless they are from research groups or, you know, highly specialized and expensive.
Okay, great. There's some questions that have come into the Q&A. Heather, did you have some of those in the Q&A that you want to bring forward?
Yeah, I was interested in asking the one about the acceptable level of uncertainty. And I think it might be good if we can step back a little bit and speak more to the epidemiologists and the health researchers on the call that might not work directly with algorithm developers or satellite products. And I was wondering if all of you could give an example of what you would consider an acceptable level of uncertainty from the satellite product, or provide an example of when or when not to use the satellite products in the context of a health study. So where do they work? Where do they not work? Drawbacks and limitations in health related work.
I'll start. Well, this is a complex question to answer. I say the short answer is it depends on the design of your health study. From what I can see, nowadays you routinely see daily, say PM 2.5 concentration estimates. Most of the data sets, if you aggregate them to weekly, monthly level, their random error drops. So what it can be sort of infer from that is the satellite-based data has normally distributed random noises. So time averaging would help you improve. And that would give confidence to chronic effect research, which is focusing on long-term exposure. So you can use monthly, trimester, annual averaged exposure estimates. As to what is, how good is good enough, I don't have an answer to that, but I guess, epidemiologists are used to sensitivity analyses. Very often we would try different model configurations, different data aggregation methods just to test if the resulting effect estimates fluctuate dramatically or not. And even better, there are ways now to kind of propagate the measurement error through the epi models. So instead of getting just the mean estimate, your effect estimate carries a uncertainty, a kind of a confidence interval. So you have a better idea if the estimate is statistically significant.
Yeah, and maybe I'll just follow up on that to say, this question of how good is good enough really does depend on the health application or the health study. But even, from almost a philosophical perspective of how do we know if a data set is good? And usually right now, the gold standard is comparison with ground-based measurements, but ground-based measurements are so limited. And Colette mentioned this in the context of PM 2.5, but it's true around the world for every pollutant. I mean, in the United States, we have a very dense monitoring network relative to other countries, and yet 2/3 of counties don't have a single monitor. And so if you're trying to think about, okay, well, let's look at satellite data over the counties that do have a monitor. Well, you still only have that monitor reflecting the air at the monitor location. So thinking about how do you even evaluate the skill of these spatial metrics relative to point-based, ground-based monitors is really a challenge. And so to me, one of the questions is, what are you comparing it with? And if you're in an area that has a dense network of ground-based monitors, then the marginal value of satellite data may be lower. But if you're looking at areas that have no monitors at all, then one of the questions becomes, well, where do the errors come from? And are there different data products and how do they compare with each other? And that idea of comparing data products with each other is a way of estimating uncertainty that is widely used in the climate community. If you think about climate models and projecting future climate change, the IPCC really looks at what's the spread across model configurations. And that this is, one way that we can start approaching satellite data products as well, because many of the instruments up in space have multiple retrievals, sort of translations of the data, so that you can compare different data products. And when you're back in our first session of this webinar series, the metaphor of a hot pot came up to think about how these surface PM 2.5 data sets are developed. I like baking, so I often use a baking and a recipe metaphor, but you have different ingredients, different models, different networks of ground measurements, and different satellite data products. And then you have different algorithms or different recipes that combine these into a usable product. And more, there's advancements in the recipes, the algorithms, and there are advancements in the data products and the models that are going in, the ingredients. And just a couple of years ago, I helped write a paper that was published in the Journal of Air and Waste Management comparing what are the different publicly available PM 2.5 data sets. And at that time, there were some that were very, very different from each other, which did not give one a lot of confidence which one is best. We're doing a follow-up analysis now comparing publicly available satellite-derived PM 2.5 at the request of the American Lung Association. And we're finding a much higher level of convergence across data sets that were developed with different ingredients and different recipes. And I think that's one way of starting to put some error bars on the inputs to the health studies. But again, whether those error bars are too big or too small may depend on what your alternative data are and what the questions that you're asking.
Could I add something too? I feel like one of the questions too, I find, is this challenge of what is the fidelity as you move to higher resolution? Again, because you're, again, introducing models or hot pot, elements or whatever to this. And then you've got these very nicely resolved maps. I think Yang alluded to that in his comments too. And you end up with this question of, should that be trusted? Do you trust the relative spatial distribution at very high resolution, right? And as I tried to point out, again, we sort of end up in this question about how do we actually validate that, and whether there is actually a path forward using, low-cost sensors in some sort of careful or, case study kinds of ways. I mean, to a certain degree, one of these questions about, especially for the PM 2.5 is, you've got to do that translation from AOD to PM 2.5, and you're going to throw in whatever ingredients you have, as sort of Tracy was talking about, but what if the ingredient list is insufficient? And so you don't know, the answers in some cases could coalesce between multiple estimates, but they may not necessarily be accurate. And it's very hard to think about how we would, again, Tracy's highlighted, there's a basic issue of even just PM 2.5 monitors and their distribution, and we need even higher resolution than that to be able to validate a high resolution derived product. So I think that is a question that I worry about sometimes, is how a user will use kind of highly resolved data that we don't really understand the relative uncertainties across that resolution space, and whether that would impact the analysis. And as Yang said, I'm sure that there's different approaches for sort of thinking about in the epidemiological study, associating uncertainties and sort of testing that. But do the products don't have that baked in, right? They don't have estimates of uncertainty that are going to vary with resolution or something like that. And so I think there's a gap between how that can be interpreted.
Not to keep piling on to the laundry list of issues associated with the satellite data products, but the other challenge that we face is that the more we're assimilating other observations and model information into these data products, the harder it is to evaluate them independently. but also apply them to evaluate models, because it becomes a little bit circular. We're using the same model to derive the satellite data product and then applying that satellite data product to assess that same model. At what point is this evaluation no longer independent? And when we get good agreement between the satellite observations and the model, is that just because that same model has been used to derive those products? So it really does add to the issue of just being able to independently assess these data products in a wide variety of ways, in a wide variety of locations and different seasons. So sorry to add yet another issue, but yeah.
Well, maybe I can spin it into a positive direction in thinking about the transition to higher spatial resolution isn't always a bad thing. Like, yes, there's the higher spatial resolution is reliant on having higher spatial resolution inputs to the products that you're using. But in terms of, say, of an evaluation or a validation, a lot of these, as you get a finer resolution, I'm going to use NO2 as an example, and I'm going to use the OMI satellite versus the TROP-OMI satellite. So the OMI satellite has 2 decades of measurements almost, and measures really at a city scale. It says, okay, over Orlando, Florida, this is the NO2 that day. But within that pixel over Orlando, NO2 is going to vary tremendously. And if you look at all the monitors that are there, they could be an order of magnitude different. And that's not wrong. Those are real patterns that are happening. And then transitioning to TROP-OMI and later satellites. So TROP-OMI measures an order of magnitude finer. So it's like 3 by 5 kilometers, 3.5 by 5.5 kilometers. And what validation is shown through these products is that the higher resolution is matching with monitors better than they did it with the previous, the predecessor satellite. So it's not saying that OMI is wrong. It's just easier to evaluate those types of spatial patterns through time. And so I guess my hope is that we're going to get better at evaluating when and how to use these data products as they improve in space and time, even though there's going to be added complexity in data volume and different perspectives and time of day.
That's a good way to end on this. One of the points you've mentioned, Laura, is in terms of interpreting and seeing patterns. And a question that came up earlier was patterns in uncertainty or confidence as you get to smaller scales. We know about how things like the surface reflective characteristics can change how well you can retrieve and infer information. We saw in an earlier presentation a separation of a comparison between NO2 and ground and satellite based on sites that were near road versus not near road, and can see where the divergence occurs there. And we have a question about the right data to, I guess, validate, and maybe background stations would be more appropriate for that. Are there any thoughts on or any evidence that about in terms of being more selective about the types of input surface for validation, or maybe even for making the soup?
Yeah, I have some thoughts, and I'm sure other panelists have some as well. In terms of like the correct data set to validate a satellite, if you want to validate whether the satellite is doing a good job in a certain area, you should be validating that in column space rather than a surface space. And there are column-based measurements out there, at least with respect to trace gases like NO2. And I'll just name one instrument, a Pandora spectrometer. And so one of the efforts that NASA and in partnership with the EPA and state air quality agencies are working on is integrating that column-based perspective where the monitors are. And so then we can say, okay, we have the satellite, how does that relate to surface? But we have this transfer standard of a ground-based sensor that, and I guess I didn't mention, Pandoras are highly accurate and precise measurements. It is not reliant on uncertainties related to, I'm not sure if the term air mass factor has come around, but it's that transition from the satellite measures the absorption of the pollutant along the path length that light takes through the atmosphere. But what is that path length? It can change on time of day. It can change due to surface properties. It can change due to, it's also important to know what is the vertical distribution of that pollutant prior. So this is getting back to the point that satellite products are not independent in themselves. They're reliant on the information that you put into them. So getting back to integrating the column perspective, you're going to have a ground truth column next to a monitor with maybe some alternative information in terms of other measurements, other species of measurements, as well as a salometer, which can measure your mixing layer depth. So you might have information as to whether the air is really stable and all the pollution's confined near the surface versus more vertically mixed through the atmosphere. And so I think there's steps being taken forward to in some areas. It's not worldwide, but in some areas to kind of learn how best to transfer that satellite to column space back to the surface.
Any other analysts want to add to that?
I guess maybe it's a small tangent, but because NO2 was mentioned, the other thing to appreciate is that the ground-based observations aren't always measuring perfectly the species that they're intended to measure. So something like the NO2 surface monitoring network is these chemiluminescence instruments that are susceptible to biases from compounds that break down within the instrument and are measured artificially as NO2. So there's also this appreciation that even if the monitoring sites are all background and very representative of what the satellite pixel is measuring, there are sometimes issues with the ground-based monitoring networks too.
Great.
I could maybe add something in the thinking about the PM 2.5 perspective as well, because I think NO2, I mean, I think the NO2 is always, it's almost like the poster child, right, for actually, something that we can really do well. And we have a good strategy for. With PM 2.5, of course, you've introduced this extra translation level. And so you can imagine sort of the question being, how do you validate PM 2.5 sort of derived from space, from a satellite product, right? And assuming that ground-based data was not used in the derivation of the PM 2.5 at the surface, then what ground data can you use? And I think that's a really interesting question. And of course, then you get into sort of the scale of the measurement, the scale of the derived product and the scale of sort of the measurements themselves, right? So, rural sites or background sites can be useful because they tend to represent sort of more well-mixed air masses, and so can be representative of a larger region, right? And so that often is kind of why people focus on those types of sites. When you get into urban conditions, the question is, again, what's the resolution of your product? And then if you have multiple, observations within a city, would those be useful to use versus just one, right? And you can imagine there can be strong gradients within an urban area. So having a single site in a city is not going to be, unless you have such a highly resolved product that you're going to actually match that location in the city, it leaves you open to some biases. But then again, there's also with PM 2.5 some differences that I think people don't necessarily appreciate, that you have both primary sources, so something like black carbon coming out of the tailpipe of a diesel engine. That is going to vary a lot spatially, right? Whether you're close to the road or, so on and so forth. But secondary, PM 2.5 is going to be much more regional in nature because it's chemically produced and it's going to have a bit of a more spread out footprint. And so it's not necessarily going to have that same kind of heterogeneity necessarily across an urban region. So, I think, if you only use the rural measurements, you would be missing an important part of the story. But using urban measurements is very tricky, I think, and needs to be done very, very carefully to think about the kind of the footprint of the measurement itself and how it's being matched with whatever you're trying to validate.
Thanks very much. So I have a change a little bit, but interesting question about the actual individual and using the information. In this case, was sort of given as an example of a patient, and how this knowledge could be translated into an individual and an action an individual might take. And for me, I think about, okay, well, that's something along the lines of an air quality index, and we did see a new product. That's a combination, I think, of models and satellites and epi data for a product that NASA is producing, Kevin Cromarn and the team. But we also hear, again, satellites in an area of data density on the surface, well, maybe not adding as much, but where you don't have data, they play a great role. Going to a little step further, we haven't talked a lot about the temporal aspect. We know we're going to see a lot more temporal information with tempo as we are now seeing with GEMS. What is the sense as to how we may be seeing really a new era of temporal information in data sparse areas that can actually be used for individuals in real time to know and take action in terms of whatever, avoid exposure, wear a mask. Certainly we can follow biomass burning plumes and know where there are and protect people better. But are the products going to come to the standpoint where they're assimilating everything and we're getting data sparse areas with hourly information that individuals will actually be able to respond to sort of in real time for their own health benefit? Is that a direction we think that Tempo will take us or others? So it's sort of temporality and the data sparse areas.
Well, maybe I'll start with this and then others can expand. But I think we're already seeing examples where satellite products are putting information into the hands of users. And if anybody here has a smartphone, you have an air quality index on that, and it doesn't turn off when you go into a county that is missing a monitor. It's always going to give you an air quality index anywhere in the world. And that's because the company that provides that data product to iPhone is called Breezometer. It's a startup company out of Israel that is using a satellite derived data fusion product to estimate global air quality around the world in real time. Now, how good is it? How accurate is it? How does it map onto all the issues we've been talking about for the past hour? That's a real good question, but it's there and it's offering something to inform individuals' use. I'd say another example is a project coming out of HACAST led by my colleague Pawan Gupta, where he's working to get the hourly aerosol data from the GOES instrument into the EPA Air Now system. And I think this is, both of these examples speak to the idea that I think satellite data are going to have the most benefit to individuals, to health communities, if they can be integrated in with the outreach and data platforms that are already being used. It's cool to go to a NASA website, but I don't think it's realistic to expect users to keep in mind, 3 or 4 different websites and have to, connect the dots on their own. I think it's going to be more powerful for us to be partnering with boundary organizations that are already providing air quality information to the public. And whether that's Air Now and the EPA or smartphones or other products, I think there are some indicators that this is already underway, and it will be exciting to see how it matures as demand and awareness grow.
Yeah, and I suppose one of the issues is that if we're going to rely on geostationary satellites to provide us with this higher temporal information, we're only really providing it over 3 large land masses, and we're sort of leaving behind the land masses that need it the most because of the absence of surface observations. So it is somewhat limited in, I think, helping the parts of the world that need the assistance the most in addressing absence of observations.
Thanks, Eloise. Heather, what have you seen from the Q&A that you want to?
Yeah, so I'm going to ask this one because I think it's so important. And this is also not an issue only in the satellite community. So that's why I think this is really important. So over time, a lot of technology changes in how we quantify the ambient air pollution. That happens in the ground-based monitors, but that also happens with the satellites when we have these new platforms and when we have algorithm development. And if you're doing a long-term environmental epidemiology study, say over a 20-year time period, it's really critical that you have a consistent metric of air pollution exposure over the entire study time period. So from a satellite perspective, when we do have all of these technology improvements and new platforms coming up, how do we make sure that we have longevity in the long-term record to look at emissions changes over time or ambient concentration changes over time? And I think the neat thing now is that because a lot of the NASA platforms incorporate all of these early adopters like at the beginning of developing this mission, I think this is getting considered with newer missions that are coming out that a lot of you are involved with. So if any of you would like to speak to that, that would be great.
I'll start. That's a great question. A lot of the users have been hesitant to take on satellite data exactly because of this concern. When you have a transition from one platform to another, NASA is not in the business of ensuring air pollution estimates consistency. That's sort of beyond NASA's mission. So, I mean, one way to kind of tackle this is for a applied group like HACAS to help with the transition. Not necessarily curating a permanent data archive, but at least put out this intermediate analyses of how the new technology compares with the old technology, because there is institutional memory living in HACAS. So we know the kind of the history and future of these sensors and why they could provide a continuous data stream. I think that should be an important mission for HACAS to take on. And then from the EPI side, it is a problem, yeah. But I've seen multiple ways of dealing with this. For example, people stratify, people do sensitivity analysis with the best data to match with a subset of their health data to see if that smaller sample size would generate something that is similar with the noisier but larger data set, right? So consensus building is kind of at the core of the EPI research methodology. You try this multiple ways in different locations. If you see similar effects, that effect's probably causal, probably true.
Thank you, Young. Does anyone else want to comment on this question? Okay,
And sorry, I might add.
Yeah,
there is a sense of urgency now because NASA is talking about the decommissioning of Terra, Aqua, and Aura. It's on the horizon right now.
I suppose maybe just to mention briefly that something that the European Space Agency does is persistently launch sort of operational instruments into space to allow for this consistency, so that they've got sort of GOM2 series instruments that measure formaldehyde and NO2. They've got the EASI instrument that measures ammonia, and they're operationally very similar, so allowing you to more easily stitch together records of observations from multiple platforms.
Yeah, I can just make a final comment, kind of connecting to what Eloise is saying, is these operational platforms that have planned missions that will be kind of continuously fed. And that, at least for NASA, those aren't typically what happens. NASA usually does, like, say, a Pathfinder puts up these satellites and demonstrates, like, hey, this is useful. And if it's a healthy instrument, it can go for a couple decades, as has been done with Terra and Aqua and Aura. And at that point, it's the operational side, at least in the US government, is transitioning that over to someone like NOAA. And then, so if we're thinking about Tempo's lifetime, the baseline mission is something like 20 months after launch. Hopefully it'll be much longer. And and that's kind of common for any satellite that goes up from NASA. But on the horizon, looking out in the next decade, NOAA has the GeoXO program, which, in addition to its standard GOES imagers that image our weather from day to day, track hurricanes, severe storms, etc., it is in the plan to have an atmospheric composition imager, which would be basically another tempo, and that is a series of missions that would go up, and that would kind of join the more operational side, like GEMS and Sentinel-4 and the Sentinel missions over in Europe.
That's really exciting to hear. Another question that's come up a couple times is talking about specialized ground-based measurements for contributing to the satellite work, and one of them we know about is the Spartan network that Randall Martin and his team has put in there. That's a good compromise of I think good quality measurements, some of it more relevant to satellite than maybe a typical ground-based station, and the role that can play. We've also had a number of times during this series of webinars talk about low-cost sensors and how they may or may not be complementary. And of course, they have their own issues, but they have the ability to monitor in data sparse areas where satellites also can play a role. What do you and the panel think about in terms of whether there really is a role to design studies where low-cost sensors and satellites are actually working in a complementary way that can advance us, particularly in data sparse areas, or it advances from other specialized surface measurements? We heard about Pandora, and the real thing being relevant, similar measurements to truly validate. Perfectly makes sense, but I guess back to health applications and exposure, we still are back to like something near the surface that might help us with the satellite. Now that this has gone on to this last session, have any of you thought more about a role for low-cost sensors here? I know satellites can help maybe sight the sensors, but can they really advance what we're doing with the use of satellite data?
Jeff, I can respond. I've been involved in some work with low-cost sensors, and I do think there's an opportunity there, but I think one, like everything else that we've talked about, right, you shouldn't, there's the importance to sort of have, people thinking about who develop the expertise related to satellite data, really sort of being able to characterize and be involved in how that data is being interpreted. And I think, frankly, you also need the measurement expertise on the low-cost sensors, right? The low-cost sensors in some ways democratize kind of this distribution of measurements and sort of encourage this whole citizen science aspect. But I think if you want to use it quantitatively, then you have to have the measurement expertise to really understand how to operate and calibrate those sensors. And I was involved in a project actually that was in Hawaii. So we were looking at the VOG associated with the Kilauea eruption, and we had a network of SO2 sensors and PM sensors around the Big Island. And, it was a, time-intensive project in terms of having, maintaining that network and calibrating that network. You couldn't just throw the sensors out there and assume that they were all operating fine. There had to be so much testing and evaluation and maintenance done to sort of maintain a network. But I think if you're willing to invest the time to do that and to involve the appropriate expertise, there is a next step opportunity there to then think about that kind of, focused perhaps deployment and a high resolution validation of satellite products, right? And what kind of measurements you could put out there, and think about how you could validate some of these derived air quality maps. So I think there is potential there, but I think it is not easy. We would love it to be, because it's low cost, we think it might be low effort, but it's not low effort. So I think that's the barrier.
Laura, others have any experience with those trying to bring low cost sensors into the mix, bring them into the soup, so to speak?
Not really with bringing in satellite observations, but at least the value overlaps with the project that we've been working on, which was making use of low-cost sensor measurements, ensuring that they're reliable. And the advantage was that they provided a far more extensive representative estimate of PM2.5 across the city that was comparable with the number of satellite pixels. So if we wanted to extend this project further, we would have a way of more reliably evaluating the satellite-derived PM2.5 product with a network of observations that's more representative of what the satellite sees.
Heather.
Well, I think we're getting close to time. We have 9 minutes left, and I think it's important that we give all of our panelists the option to give everyone a takeaway message. So if each of you could provide one take-home message on using these satellite-derived air quality products for health applications, that would be great. Why don't we start with Tracy?
Thank you, Heather. I guess my takeaway is that, we're talking about a lot of issues here. And sometimes it can say like, oh, we don't know if it's right. It's a column. It's so hard to use. But the truth is we're not going to be solving these problems if we don't have health researchers actively engaged in this community. And so I guess I would just encourage folks on the call to, whether they're already using or not using satellite data, to get involved with the conversations around appropriate uses and potential next steps, because without the voice of the users, it's hard to be moving analysis forward. And I just want to issue an invitation. The HeyCast team that I lead and Yang is on really has a mission of trying to make these data available and answer questions. And our website is haqast.org. We have a meeting that will be broadcast from Houston, June 1st and 2nd. We have another meeting in Madison, Wisconsin, October 20th and 21st. And all of these meetings are really intended to be an open door and a welcoming environment for health users. So please, if you have questions, I hope, whether through HEI, through any of us personally, through joining our community, that I just encourage folks to get involved, because this is such a growing field. We need your voice.
Thank you. Eloise, would you like to go next?
Yeah, I think I'll just reiterate what I said at the start in the introductions, that it's vital to work with the community that's developing the satellite data products all the way from the start of the project, and to also do the due diligence of reading the copious peer-reviewed publications and the lengthy retrieval documentation and the README files, so that you're well informed when you meet with the satellite data product developers, so that you can have an informed discussion around the uncertainties, the application limitations or opportunities in using the satellite data products to address the many uncertainties we have in understanding air quality and the impact it has on health.
Yeah, thank you. Colette?
Sure. I think, we maybe focus a little bit today on the pitfalls, but of course the satellite, data does, give us huge opportunities, right? But they go hand in hand. And I guess I would just make a plea that I think it's really important that the developers of data products really carefully characterize the limits of their approaches and the products, because I think we should want that data to be used wisely, and also that the efforts of the health community not be abused in some sense, right? So we need to, I think, ensure that that is communicated, this we know well, this we have more uncertainty on, so that really when I think someone in the health community trying to make that decision of, am I going to invest the effort into incorporating all this data in my analysis, they can be really well informed about the quality of the data. And satellite data is great, but it is not going to answer all of the questions that people are going to want the answers to. And so we have to be humble, I think, in that regard.
Yeah, thank you, Laura.
Yeah, I think a lot of my final thoughts kind of follow on to what Tracy, Eloise, and Colette said, in that I guess what I would say is thinking about in health applications, which I don't have a big background in, but I have a background in the physics of the retrieval. Have an idea in mind when you reach out to people as to what quality of data are you looking for? Do you really just need gradients? Do you need what time and space resolution is actually going to be helpful? And when you have that conversation with the data provider, they would be able to tell you whether it is or isn't possible, or suggest alternative ideas. And I guess the final message that I would give is to not hesitate to reach out. and maybe don't feel isolated and alone and overwhelmed, because it's always overwhelming. As somebody who's familiar with trace gas, I find aerosol data can be very overwhelming. And so I would go talk to somebody like Colette when I want to use something like that. And so just recognize that you don't have to be an expert in all, but to recognize the expertise that you need in building a team and making sure that you have all those aspects covered.
Yeah, thank you, Yang.
Yeah, thanks, Heather. 2 points to make. First, I guess what the audience is seeing is normal, and it's part of the healthy development of this new field. And so don't be discouraged by all the caveats, all the cautioning, all the debates, confusion, all that. It's just, this satellite data application is at this stage. It's still very young. It's at this stage of people sorting out things, figuring out their applications, their innovative applications. And the second point I want to make, especially a call to the audience, is be a part of the movement. The technology development has been driven by users in a very powerful way. Where it goes, it's going to be shaped by the users. So instead of sitting back waiting for it to mature, be a contributor. Be part of the direction where this is going.
Yeah, thank you. That's great. Jeff, would you like to give any closing remarks?
Sure. Thanks so much to the panelists. It's been a great conversation, and also I want to thank all the speakers we've had across these different webinars. I think they've been incredibly complimentary, and I hope that everyone here will point towards what's on the HEI website. Now, I think a question and a conclusion I've reached in my mind is that really the satellite information has provide us with a step function change in what we can know and see, and I mentioned that at the first session. In terms of this question about how we reach the promised land that Hoff and Christopher asked quite a few years ago, I would say yes, we have, but there's a whole community that we want to be part of to keep redefining what the promised land is. But it's been a step function change so far. We've heard satellites information, I think now clearly mentioned as it's not a measurement of ground air quality, it's a product. We've also heard it called a soup, a metric, data, a tool, air pollution estimates, qualitative products, merged data products, everything besides a measurement of air quality of the ground, because it's not that. It's many things, many useful things that we know about for sure. And we don't want to ask about what it can't do, but we continue to think about what we can do with it. And there's been, I think, examples we've seen in this series of webinars about some really creative use. One example I can recall is Sally Swade's presentation showing, looking at the tropomi data, on weekdays and weekends, and referring something really meaningful about diesel exposure inequities that happen that could be inferred from that. So I think that there's sort of no limit to creative use. Matt Cooper has looked at how we might infer differences in how lockdowns affected air quality in different parts of the world. So I expect lots of good surprises to come from creative researchers out there. Now, it is a soup. Much information gets brought together. That's going to necessarily have to continue as we start to look at tempo data, and we have all the advantages that tempo and Sentinel-4 and GEMS are bringing, but there's always clouds, there's always nighttime. So there's always a massive extrapolation to other times and locations, and that those massive extrapolations are going to have to continue as we develop more and more uses for these tools. And we want to forget that, and we want to understand, I guess, what those mean in terms of the different applications that we bring forward from them. But it's no doubt that we truly do have a very valuable eye in the sky. And in terms of health applications, it's hard to dictate exactly what health research question or health research product can use what satellite product. Those will continue as people collaborate together for sure. But I have no doubt with the richness and of the information that's coming out now from satellites combined with other things, and the coverage it offers, that the awareness is coming from everybody, and we all know that more awareness of air quality risks that satellites have helped contribute to, really I think can only improve health in terms of people being aware and knowing what the issues are, whether it be more pressure to control air pollution or individual actions to protect yourself. So I think there's been a huge movement forward in this, and I look forward to continued work with more satellites going forward. Thanks again to everybody, and I turn it back to Allison.
Thank you, Jeff, for this helpful concluding statements, and thank you to all the speakers and chairs for this informative and inspiring discussion, and to all the audience members for your engagement, and also all the HEI staff who've been working on this workshop behind the scenes. So we hope that you found this workshop informative in your understanding of what air pollutant and remote sensing from satellites can and can't do for air quality exposure assessment and health studies. This is meant to be an interdisciplinary exchange of ideas. The next step for the research committee will be to consider the materials shared by the presenters, during the discussions, and by the audience during this workshop. So if you would like to contribute more to that discussion, please do fill out the survey linked on the slide. And so we'll use that information to discuss how best to move HEI more into some of these areas and where we can contribute best. So we'll be in touch at some point with our next steps there, whether it'll be funding more research or convening or writing up summaries. You'll be hearing from us. And so we'll also be updating the resources document on the webpage for the workshop with additional materials that were recommended by the workshop attendees or by the speakers or panelists for any session. And you're welcome to get in touch with us at any time if you have any questions or suggestions. To stay informed on HEI's work related to satellite, either share your information on the pre-workshop survey or sign up for newsletters at our homepage. The slides and recordings from all 4 sessions will be posted on the HEI website. The first 3 sessions are already up there, and this session will be posted in about the next week. And if you'd like to stay more involved, we'd like to invite you to HEI's annual conference to be held in Washington, D.C. at the end of June. You can find more information on the sessions and registration for in-person or virtual attendance at the HEI annual conference website shown on the slide and in the chat. Thank you all for joining us and contributing to this discussion. And I look forward to exciting ways that we can contribute and continue this discussion moving forward. Thank you.